back to this discussion on performing a chi-square goodness of fit test, and we are going to be demonstrating this technique in a tool which is going to be Python. So when you are going to perform a chi-square goodness of fit test, we first need to know what are the steps that you are going to follow. So in general, we are going to have these steps. So in step 1, we are going to get descriptive statistics. And using these descriptive statistics, we are going to narrow down on some possible candidates for the population distribution. In step 2, we are going to use visual tools to further check whether whatever we have identified in the descriptive statistics match with those that we have got through visuals. So both these steps primarily focus on narrowing down on possible guesses for the parent distribution. So that is going to be step 1 and step 2 that we would be performing. Next, in step 3, we would actually start creating the frequency table that is required. Then later on, in step 4, we would make appropriate conclusions. Right? So here we would basically be creating the frequency table, computing the test statistic, and so on, and then we will be using it in step 4 to make a conclusion of whether we are going to accept or reject the null hypothesis. So this is going to be the 4-step procedure that you would be seeing in the tutorial that we are going to do. Having said that, before I start on the Python tool, please note our goal here is to not expose you to coding, though we would be asking you to do a few bits of these codes on your own in future videos, but our goal is to show you these steps, to demonstrate these steps on the tool. With that being said, the code would be given to you, it would be available for you to use. We would now focus on implementing those steps that we just saw. Okay. So in the first step, in any tool that we are going to use, we need to load the necessary packages, the basic packages, and then the data set. So let me just load the data set into this tool. Okay. So for this demonstration, I am going to use this data known as the data underscore uniform, and as the name implies, we are going to be demonstrating this tutorial for a parent distribution that is, let's say, following a uniform distribution, and appropriately we have got a data from that parent distribution which is the sample, and that is data underscore uniform. So I have loaded the data into my Colab environment, and I am importing the two basic packages, which is NumPy and Pandas, and then I am loading my data set into my environment, which is going to be read in this variable known as df, and this df has 51 observations and 1 column. So this, let's say, is going to be the length of a scratch in millimeters on a car that is manufactured. Millimeters, microns, however you want to use it, whatever unit, but they are going to be length of scratches. So we have 54 mm, we have 52 mm, 51 mm, 53 mm, so on and so forth. Like this, we have 51 observations, and that comes under this head known as the OBS. The first column is your index column. So 0 to 50 would be your index, and for each of these index, the length of scratch is being given. Okay. The first visualization that we are going to do is to plot a histogram for this particular data set. So let's plot that, and these are the commands for you. So if I plot this what do I see? I see that there is not one single peak. I do have a peak here and here, so there are several peaks. So it is looking non-Gaussian to me, but some people might call this as a normal distribution as well. Let's say they could say that these two are just anomalies and it is going up and coming down. But however, these values are always 4 or more, right? So majority of them, the values that are less than 4 are very minimal. Most of them are 4 and we go up to 10, the frequency, right? So we could have either a normal or a Poisson. So those are the two possible content. Poisson, sorry, not a Poisson since it's continuous, it could be a uniform, right? So these are two possible basic contenders for us. So let's keep that in mind from the visualized data. So from this plot we see that it could either be a normal or it could be a uniform. To narrow down further, let's do some descriptive statistics. So what do I get? I have a count which is 51. I have a mean of around 55. So that is the mean. The standard deviation is extremely low. So we have around 2.6. The minimum value is 50. The maximum value is 59. And the different quantiles 25, 50 and 75. So 50 quantile is basically going to be the median. Some people might be interested in the variance, the skew and the kurtosis. That also you can get. So the variance is going to be the square of your standard deviation, right? So now, having looked at this, we can say, okay, given all of these values, I will leave the interpretation of the skew and kurtosis to you. But given all of these interpretations, we can say, all right, this is not going to be a Gaussian distribution. So the alternative is going to be a uniform. So we would proceed from this step. We have narrowed down from, let's say, Poisson, uniform, binomial, normal, so on and so forth, to a possible contenders as normal or uniform, and from that we are taking this as, let's say, a uniform and proceeding further. Now, based on visualizations and some descriptive statistics, we are telling it's uniform. We need to perform it with a test and conclude that it is uniform. So for performing the test, we are going to import all of these statistical packages for us. Once we have got the statistical packages, we can further check whether our guess of uniform is good or not using something known as the QQ plot, the quantile plot. So the quantile plot is going to check whether the proposed distribution and the theorized distribution, or whether the observed distribution and the theorized distribution are matching in their tail portions, right? So if I plot a QQ plot, and if all of these values fall on this 45-degree line, then my theorized distribution and the actual distribution are matching perfectly. If not, if there is very high deviation, then I would say that my proposal and the theorized are not matching at all. In my case, most of the points are falling on this line, and a very few points, most of them are falling, and a very few points are deviating from this 45-degree line. And hence I can be certain, with certain amount of confidence, say yes, my uniform distribution, my assumption of uniform distribution fits well for the population given the QQ plot. However, the QQ plot only checks whether the distribution is fitting well on the tail regions. If I have to do the same thing for checking them on the center regions, I go for something known as the probability plot, which is the PP plot. So if the PP plot, all the points fall on this 45-degree line, then the center of the distribution that I am proposing and the center of the distribution of the theorized population also matches. And in this case, what I see is most of the points also fall on the line, and very interestingly, the deviations that happen in the QQ plot and the deviations that happen in the PQ plot are exactly in the same area, right? So they are falling in the 0.6 to 0.6, 0.6 to 0.6 in both the PP and the QQ plot. And this type of deviations will happen only if the population is a flat line, which is going to be a uniform. So my assumption of uniform for the population is actually a good fit, can be concluded from this. Just as an exercise, do one thing. In this QQ plot, instead of stats.uniform, use a different distribution, stat.poisson or something else, and you will see how erratic this line or these points are around the 45-degree line. So that I would leave it as a self work for all of you to do. Now, after doing all of this, the histogram, the descriptive statistics, the PP and the QQ plot, I can tell with certain amount of certainty that this distribution is indeed coming from a population which is uniform. But these are all descriptives and visualizations. I need to perform the chi-squared goodness of fit test, get a test statistic and tell with statistical significance whether whatever I have told using visualizations is true or not. For that, we would start performing the chi-squared goodness of fit test. And just a recap, in my previous video I didn't tell you what is the null and the hypothesis. So here we see that the null hypothesis for the chi-squared goodness of fit test is that the given data follows a uniform distribution, that is, the population follows a uniform distribution is the null hypothesis. And the alternative is that the given data does not follow a uniform distribution, which means what? The original parent distribution is non-uniform in nature. So that is going to be the alternative. So this is the null and the alternative for us. And the first step in performing the chi-squared goodness of fit test is to create the frequency table, and the first step in that is to identify the bins. So what I am going to do is I am going to cut this entire distribution into bins of equal length. So what I am doing is, based on the minimum and maximum value, I am using this command called pd.cut, which is going to cut this entire data frame into bins and going to assign each of these observations for a particular bin. So my first bin is going to be, my first observation is going to fall in a bin which is going to be of length 54.082 to 55.018, and each bin is going to be approximately of the same length. So you calculate the length, it should be coming to around 1.3, right? So 1.3 to 1.4. So each of these observation now falls into a particular bin. And in step 2, I am creating a new data frame called df2, and for each bin that I have created, I am going to find how many observations falls into that bin. So that is going to be, df2 is basically going to be representing my frequency table. So in bin 1, which is going to be 50.33 to 51.26, there are going to be 4 observations in my data set, right? So if I just open this uniform data set, right? So so if I add a filter and I want to do a number filter, I will now type the bins into this. Since it's an open interval, it's going to be greater than and is less than or equal to, I see 4 observations in the sample, and that is why for each of these bins the number of observations is going to be varying. So 4, 6, 5, 5. So if I similarly as an exercise do it for the data set that is given to you, check for this bin whether you are getting 5 observations, for this bin whether you are getting 10 observations, right? So this is going to be the observed frequency. Now using this, I must now compute the expected frequency, and for a uniform distribution there is something very beautiful that will happen. So what is a uniform distribution? It's going to be the the histogram for a uniform distribution, if it's exactly right, should look like this, correct? Every value has equal number of observations. So this is frequency, and let's say this is the range, right? So if I plot a histogram for a uniform distribution, a perfect uniform distribution, then every value or every bucket should have the same number of observations, right? So if I have to do this, then the probability in each of these is going to be the same. Let's say this is going to be x1, this is going to be x2, this is going to be x3. The number of count over here is going to be x, right? So x1 is going to be equal to x, x2 is going to be equal to x, x3 is going to be equal to x, so on and so forth. Let's say this is the kth bucket, xk is going to be equal to x, which means the probability in each of these is going to be x by n, since x1 plus x2 plus so on up to xk is going to be the number of observations that you have. The probability space under each of these bins is going to be the same, x by n, which means what? The value for all of these is going to be the mean value of your sample. So if I take 4, 6, 5, 10, and if I take the mean of these values, that is going to be the expected frequency in any given bin, because the distribution is uniform, correct? So that is going to be the expected frequency in each of these bins. So now I have created my probability table, my frequency table. For I have got different bins, and for each of these bins I have got an observed frequency and expected frequency. Now all I have to do is perform the chi-squared goodness of fit test. So I will use this command known as chi-squared, and I would feed the observed frequency and expected frequency into this, and I would run it. So once I have run it, I would get two values. The first value is the computed chi-squared test statistic, which is going to be 6.45, which is nothing but observed minus expected the whole squared by expected for each bin, summed up for all of the bins. That is going to be this value. As a self work, compute it for this particular frequency table and see whether it is matching, right? So this is going to be that value, and the second value that I get is the p value, correct? So now that I've got these two, I can use any one of the two methods to make a conclusion. Let's say I am going to use the first technique, which is going to be based on the p value, right? So if I have to conclude based on the p value, what I have to do, I have to compare this value of 0.694 with a level of significance alpha, and if this 0.694 is less than the alpha, I would say reject the null hypothesis, which means I would say that the population does not follow a normal, right? So in our case, let's take an alpha of 5%, which is 0.05, and since this value of 0.694 is greater than, in fact very greater than 0.05, I would conclude do not reject the null hypothesis, which means I would say that the population is indeed following a uniform distribution, because I have got a sample that is telling me not to reject the null hypothesis, right? So that would be the conclusion. And when you use a p-value, you can do something one step further. You can actually go to a level and say that up to a level of significance of 0.7, because only at 0.7 this p-value will become less than the alpha, right? So up to a level of 70% or 0.7 significance level, I would not reject this, I would not reject my null hypothesis for this particular data set. Tomorrow if a data set changes, again I will have to do a p-value test and conclude and then arrive at a significance level, but given this sample, up to a level of significance of 70% or 0.7, I would not reject the null at all, and up to that level I would say that the population is indeed following a uniform distribution. So that is the added advantage that you get when you do a p-value test. Of course, I could do comparison with a tabulated test statistic, And for that, what I do is I use this command called chi2.ppf and input the 95% confidence interval. So 1 minus alpha value, so that is going to be 0.95, and for 0.95 n minus k minus 1, which is the degree of freedom, which is k minus p minus 1, which is going to be the number of bins 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since I am going to split this into 10 bins, so 10 minus 2, since for a uniform distribution I need two parameters, the lower value and upper value. So 10 minus 2 minus 1, so that is going to be 7 at a level of significance of 95% or a confidence interval of 95%, and with 7 degrees of freedom. The tabulated value is going to be 14, and since this tabulated value is greater than my 6.4, the tabulated value is greater than my 6.4, I would not reject the null hypothesis, and hence I can conclude that the original parent distribution is indeed coming from a normal, indeed coming from a uniform, since I am doing it for a uniform. So this is how you perform the chi-squared goodness of fit test in Python. So this tutorial we will stop it here, and in the next tutorial we will see the same technique with a few catches that would be happening in for a different data set.